All right, so we'll continue then and start talking about the concept of electricity. So obviously we're interested in electricity. We're interested in the electricity in semiconductor devices. How a current moves through a semiconductor device. Just to remind ourselves, electricity is a movement of charge. Okay? If you have static charge, that's not electricity. Okay? The charge has to be present and the charge has to be moving. So electricity generally behaves on the movement of electrons. What we're going to find out in semiconductors is that there is also something called the absence of electrons, which is called a hole. Okay, but the fundamental actual particle particle involved in electricity is electrons. Okay. Since electricity is a movement of electrons, if we want to find out the electrical behavior of a material, we have to start by knowing where the electrons are and in which direction they move. So this module is sort of answering the first question, where the electrons are located. So we're going to talk about methods to figure out where the electron is, and we'll also talk about methods to see how much energy the electron has. And we're going to introduce the concept of energy band diagrams, of orbitals. We'll get more into energy band diagrams next module, but here we're going to talk about the basic concept of an energy diagram. All right, modules 3 and 4 are going to get more into how electrons move through semiconductor materials. So starting off with the location of the electron. Has anyone heard of the Heisenberg uncertainty principle? Some of you have, so you've taken through courses in quantum mechanics, I imagine?
The Schrödinger's cat.
Okay. Schrödinger's cat is a good book. I haven't read it myself, but I heard Schrödinger's cat, they talk about some of these concepts. Okay. So right now we're interested in knowing where the electrons are located. And one of the fundamental things about the Heisenberg uncertainty principle is that it's saying that it's impossible to simultaneously measure both the momentum and the exact position of an electron. Okay, and to understand where the Heisenberg uncertainty principle comes from, we have to get more into quantum mechanics, which is not the focus of this class. We're going to focus on what it means in terms of semiconductor devices and orbitals and probability density functions and so on. This is a slide that was contributed by one of the students in winter 2014. It says, the electron, it's a proton. Where the hell are you? And the proton says, that's a toughie. Yeah. And I can tell you where I probably am. Does that help? So that sort of encapsulates this concept of the Heisenberg uncertainty principle. Instead of saying that the electron is at this particular point in space, we can say that there's a certain probability that the electron is within a volume. Okay. So what we can say then is, let's say we have some sort of volume like this. What we're going to do is say there's a certain, for example, let's say a 5%, a 95% probability that the electron is here. Here meaning within this volume. That's how probability functions work. Okay, we can't specifically say the electron specifically in this location. So you'll have a problem on the Heisenberg uncertainty principle. It says there's something called the position uncertainty and there's something called the momentum uncertainty. So this is the position uncertainty here, delta x, the momentum uncertainty, delta p. Now, momentum is mass times velocity, right? We know the mass of an electron. The mass of an electron is defined. What's uncertain is the velocity of the electron. So we can't know the position and the velocity of the electron at the same time. So the Heisenberg equation says that the position uncertainty multiplied by the momentum uncertainty is greater than or equal to Planck's constant divided by 4 pi. Yes?
So if we were to theoretically take an electron down to absolute zero and like just take all mg out of it, and would we be certain that it would have no speed? And then could we tell exactly where it is with 100% certainty?
You can do that. Because you use electrons to measure the speed and the position. So
If the electron is not moving, it's impossible to detect it. That's one of the problems. Sometimes when we're trying to detect electrons, we have an electron detector, which consists of two parallel plates, and between those parallel plates we put a voltage, so the electron gets accelerated in one direction, and when the electron deposits itself on a plate, it creates a small current. Yeah. So you're talking about experiments in physics, which actually I'm not as familiar with, but this is one of the issues that you probably run into. Yeah. So instead, we can so like I said, we can calculate the probability that an electron will be somewhere. So getting into probability density functions then. Since we can't determine this precise location of an electron, we have a wave function that tells us the probability of finding an electron within a volume that we specify. So that's getting back to this diagram here. We can say that here's some sort of volume, and we can say there's a 95% probability that the electron is in that volume. So this is what the wave function tells us. The wave function is a probability density function, and when integrated over a volume V, it tells us the probability of finding the electron within that volume. Okay, this will take you back to multivariable calculus. Most of you have taken that class. How many of you enjoyed the class? Some of you. Okay, that's good. It's an acquired taste. It's like fine wine or good beer. You know, it grows on you over time. I disliked it the first time I took the class. The more and more I've been using it, a couple of years ago I was teaching electromagnetics and used a lot of integrals in that class. For those of you who maybe have taken Professor Michael Wu's class in electromagnetics, you use a lot of integrals to figure out what the electric fields are. In any case, the wave function, a probability density function is this function psi here. Okay, and when you integrate this function over 3 dimensions, you get a constant, or you get a scalar. The scalar is a number between 0 and 1, and that tells you the probability of finding the electron within the volume. Remember with remember with 3-dimensional integrals, you're integrating over a range of x, a range of y, and a range of z, right? So when we're doing the probability density function, we would integrate from, let's say this is x, goes from 0 to, this is x equals 0, this is x equals 1, this is y equals 0, y equals 1, and this is z, and this is the y equals 0, y equals 0, y equals 1. All right, so by this formula, the probability of the electron being within that volume would be this probability, P of E, would be equal to the integral from x equals 0 to 1. Let's zoom in here. Integral from y equals 0 to 1, and z equals 0 to 1 of this function psi, and you take the absolute value of it and you square it. d, z, dy, dx. So this is the integral that you'd solve, and this would be a number between 0, so it would be a number between 0 and 1. Okay, that's what those brackets mean. It ends up being a number between 0 and 1. Okay. So, yes, getting back to this then. As with any probability density function, if we integrate it over an infinite space, the probability of finding an electron is 100%. Okay, if an electron exists somewhere, if we integrate over the entire space, all x, all y, and all z, then of course the probability of finding that electron is going to be 100%. So that's where that part represents. That's what it means when you have a triple integral And then here you have the infinite. So you're integrating over the infinite domain. All right, so what is a probability density function? The best way to understand it is to just go through a few examples here. There are discrete probability density functions, and there are continuous probability density functions. And so some of you have taken a class in probability and statistics. Some of this stuff may look familiar to you. So let's say we roll a die. What's the probability of rolling a 4? 1 over 6. Why is it 1 over 6? There's 6 faces on a die. And so the chance of rolling is of selecting one face, which is 4. The probability of that would be 1/6. So that's obvious. Now let's say I pick an integer between 1 and 10. What's the probability of choosing a 6? 1 over 10. There's 10 different possibilities, and we're selecting one. The probability of selecting 1 out of 10 of those items, the probability is 1/10. Okay, now let's say I pick an irrational number between 1 and 10. What's the probability of choosing a 6?
0.
I heard it. It's 0. Why is it 0? There's an infinite number of possibilities. When I say any rational number between 1 and 9, or 1 and 10, it means like I could choose 6, I could choose 6.01, I could choose 6.0001, and so on. There's an infinite number of possibilities in there. So this sort of explains, or it lets you see what the problem is when we're talking about continuous systems or analog systems. The first two examples were discrete systems, where there's a finite set of possibilities, rolling a die. In the real world is analog, right? Unless you're talking about certain types of quantum mechanics. We'll get into that later. But right now let's talk about probability density functions. The real world in general is analog. There's an infinite number of temperatures that there could be. There's an infinite amount of pressure in the atmosphere, and so on. So the probability of choosing a 6 here, the answer is 0. What you have to do when you have these types of, when you're working with analog systems where there's an infinite number of possibilities, is that you have to do something like this. You say, let's say I pick a rational number between 1 and 10. Now I'm going to ask, what's the probability of choosing a number between 6 and 7? So any rational number between 1 and 10, what's the probability of choosing a number between 6 and 7? You think about this one for a second. So if we imagine that we have so we're picking a number between 1 to 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's move that 10 over here. All right, 1, 2, 3, 4, 5, 6. So this is 6, and this is 7. So we're saying the probability of choosing a number between 6 and 7. 1/9. Right. It's the area of this region compared to the whole region. Right, if we think of these in terms of units, this is 1 unit, and then there's 1, 2, 3, 4, 5, 6, 7, 8, 9 additional units. So the probability between 6 and 7 is equal to 1/9. So you see, like in analog systems, we have to pick a range. We can't pick a specific value, we have to pick a range. So this is what we're getting at here with the electrons too. Remember I was drawing this picture up here. We have to pick a range of values. We can't say that the electron is exactly at this particular XYZ. We're going to say that there's a probability that it's within this range of values. So a couple examples of probability density functions. There's a uniform PDF. The uniform PDF is if you have a completely random distribution. There's no bias towards anything. Okay, so what's the probability that an electron is between x equals 4 and x equals 5? So if there was a uniform probability, that means there's an equal probability that the electron could be in anywhere of those regions. In other words, the electron is not, there's no preference for the electron to be in certain regions compared to others. What could cause an electron to preferentially be in one place versus another? I'm sorry?
Charges.
Charges, yeah. If there's charges involved, the charges can repel, like charges repel, opposite charges attract. So the existence of different charges and different electric fields can cause the electrons to be preferentially in one area versus another. Okay, but starting with the most simplest example, a uniform probability density function would say something like that the electron can be anywhere. This is a one-dimensional example, by the way, to simplify things. In an actual situation, we'd be dealing with three-dimensional functions. So there's a probability, the probability that the electrons at any given point, the probability density function would actually be a three-dimensional function of x, y, and z. But we're just doing a one-dimensional function just so you can sort of get an idea. So the uniform probability density function, what is the probability that the electron is between x equals 4 and x equals 5? 1/5. That's correct. So what we do, and this is getting at how you integrate probability density functions. We can kind of look at this and say, well, the area of this region is 1/5, and the area of the entire thing is the area is equal to 1. Okay. So this p of x is a probability density function, and this has a value of 1/5 between the values of x equals 0 and x equals 5. If we want to find the probability that x is between 4 and 5, we would take the probability, the integral, if this pen works, p of e equals the integral from x equals 4 to x equals 5 of 1/5 Yeah, it doesn't seem to like it when I do this. All right, let's use this one instead. So the probability of finding an electron between 4 and 5 is equal to the integral from x equals 4 to 5, and the function is 1/5 dx. This is a probability density function. So this function is 1/5 times x, and we take that from between 4 and 5. This is 1/5, 5 minus 4. So this probability comes out to 1/5. Okay, does this make sense? Just doing a simple integral here. Get rid of that. Anyway, the area of the entire region has to equal 1. In this case, the entire domain is between x equals 0 and x equals 5. So if we integrate over the entire domain, then the integral must add up to 1. So you can see here that that would indeed be the case. The non-uniform probability density function is when there's a preference for the electron to be at one place versus another. Like I said, this could be caused by the fact that there are charges around. This could be caused by, in a lattice. This might be because there's nuclei. Nuclei can be positively charged, right? The electrons may be attracted to those nuclei. They're going to be shaped by the electric fields. Suppose there's multiple atoms in a lattice, like we talked about with the shape of silicon, right? There are multiple nuclei, and those multiple nuclei can create electric fields, and therefore change the location that the electrons are most likely to be. So the non-uniform probability density function will look something like this. What will remain the same is that the area over the entire domain will still equal to 1. Okay, so I see here that I pointed out that the area here is equal to 1. The area under the curve over the entire domain must equal to 1. In this case, what is the probability that the electron is between x equals 4 and x equals 5? 0. Exactly. So this is a non-uniform distribution. All right, so now getting into the Schrödinger equation. So here we were talking about this function psi, this one right here. There we go. So this function is what we're going to be talking about now. The Schrödinger equation, it originates from classical mechanics. It's a quantum mechanical law describing the energy of an electron in a given potential field V. It allows us to find the wave function psi. The origin of the wave function, we're not going to get into the mechanics of this equation or how to solve it. We're only going to look at a few examples of solutions to the Schrödinger equation. The basic statement of the Schrödinger equation has to do with the energy of an electron in terms of classical mechanics. So the energy of an electron is equal to its kinetic energy. The kinetic energy has to do with how fast it's moving. And the kinetic energy is simply E equals mv squared over 2. Right, so the kinetic energy rewritten in terms of momentum here is p squared over 2m. Here. Now, the electron also has potential energy. Now that potential energy is denoted by V, and that gives the total energy. All right, the kinetic energy to you may seem pretty straightforward, right? A moving object has kinetic energy. That you remember from physics. Does anyone remember how this potential energy works?
Depends on the energy level and on the distance away from the floor or something.
Distance away from what?
From the floor.
From the floor.
Due to gravity.
Ah, due to gravity. That's an example of potential energy, right? Does everyone remember this classical example of gravitational potential energy? So let's write that down. So gravitational potential energy. So we have this hill, right? We have this little horrible-looking car there, right? At the beginning of the hill, the car has a lot of potential energy, right? But it may not be moving yet, so it has zero potential energy.
You mean zero kinetic energy?
Yes, sorry. No kinetic energy, but it has gravitational potential energy. All right, as this thing is going down the hill, the gravitational potential energy is converted to kinetic energy. All right, so when it starts moving the hill, there's a lot of gravitational potential energy. The amount of gravitational potential energy goes down the further you go down the hill, but the amount of kinetic energy increases as the car accelerates as it's going down, right? So the maximum kinetic energy is at the bottom of the hill, but there's no gravitational potential energy here. Now, there's a similar situation that arises in electronics, and you've seen this before too. So we call this electrostatic potential energy. And this situation is really quite the same. We have a voltage source here. All right, if we put a voltage source across two plates like this, what happens? It's capacitance, that's right. So I heard that there's a charge also. We have a buildup of positive charge on this side. and a buildup of negative charge on this side, we end up with an electric field that points this way. Now let's say I put an electron here. What's going to happen to that electron? It's going to move towards, right, it's going to move towards the positive. So at this point, the electron has maximum, we'll call this electrostatic potential energy, and it has no, let's say it has no kinetic energy at this point. The electron moves here, and by the time it gets to this point, now it will be accelerated, right? So at this point it'll have maximum kinetic energy and no electrostatic potential energy. That electron is accelerated. It's just similar to that wheelbarrow going down the hill. When we talk about electrostatic potential energy, so electrostatic potential energy is a volt. We talk about volts. 1 volt is equal to 1 joule of kinetic energy per coulomb of charge. So joule is a unit of energy, and coulomb is a unit of charge. Okay. Similar type situation. So going back to the Schrödinger equation, I want you to understand that electrons have a certain amount of kinetic energy that has to do with their speed, and they also have a certain amount of potential energy, which is given by their voltage. That's V. That gives a total energy E. Now, if you apply quantum mechanical operators, and this is the part we're not going to go into too much detail on, if you apply quantum mechanical operators, you can rephrase this equation in terms of a partial differential equation. Have any of you taken class? You've taken classes in ordinary differential equations. Has anyone taken classes in partial differential equations? Great. So ordinary differential equations are where there's a derivative with respect to time, or there's a derivative with respect to a single variable. Partial differential equations are equations where it's a differential equation where there's derivatives with respect to space, dx, dy, dz. And in addition to that, there can also be derivatives with respect to time. The quantum form of the Schrödinger equation, it's a partial differential equation of this variable psi. Okay, you can see that this kinetic energy has been expressed in this manner. The potential energy has been expressed in this manner, V times psi. And this is equal to the total energy here. Now, this del operator is a gradient operator. This might look familiar to some of you from multivariable calculus. This H that has a little line through it, that's actually a form of Planck's constant divided by 2 pi. All right, like I said, we're not going to go into how to solve the Schrödinger equation. We're going to just understand a little bit about how it works. If you want to understand more about it, you take a class in quantum mechanics. So how's the Schrödinger equation used? Given some potential field, the solution of the Schrödinger equation gives this wave function, psi. And that psi describes the location of an electron, where to find an electron. All right, so if we look back at this equation, what are the inputs? H is a constant, M is a constant. All right, these are also constants. What's the input to the function is V. V is a function, a three-dimensional function. It's the electrostatic potential. Now, I can give you a simple example of electrostatic potential just by looking at this thing here. In this particular thing that I've drawn, where is the electrostatic potential the highest? By the bottom plate, right? Right. So imagine the system in 3 dimensions, okay? Just think about it qualitatively. The highest potential, the highest electrostatic potential is going to be near the bottom plate, and it's going to decrease linearly as we go to the top plate, okay? So it's a 3-dimensional function. So this V is a function of x, y, and z. Wherever there's negative charges, the electrostatic potential can become large, and vice versa. Actually, electrostatic potential is described in terms of positive charge, but I'm just trying to describe this to you in the sense that the electron has more energy towards the negative. So we're really talking about the absolute value of the potential energy here. So you have this three-dimensional function v of x, y, z, which describes the electrostatic potential in spaces, and that's determined by where the charges are located. You plug that into the Schrödinger equation as a boundary condition, and the solution to the Schrödinger equation is a wave function psi. It's also a function of x, y, z, and as we showed before, if you integrate that function psi over the 3 dimensions, you will get the location of the electron. So this is the connection between the atomic structure and the electronic configuration. We started this lecture off by saying that the atomic structure of a material determines its electronic properties. This is mathematically how that happens. The atomic structure of the material determines the potential field, the V of x, y, z. So what might a structure look like? Well, we've talked about this before. You know what the atomic structure of silicon looks like, and we covered that in our last lecture. So it might be something like this, where you have a nucleus. This is a silicon atom. This is another silicon atom. Each one is connected to 4 others around it, and this lattice continues. Each one of these circles in this diagram represents a nucleus. So the nucleus has positive charge, right? It consists of protons and neutrons. Right? Wherever you have charges, there's an electrostatic potential field there. There are also electrons around each of these nuclei, so those also contribute to the electrostatic potential field. So the atomic structure of a material determines this potential field, V of x, y, z. That's a boundary condition to the Schrödinger equation. When you solve the Schrödinger wave equation, it's a partial differential equation. It can be solved using a variety of methods. The answer that you get is a wave function, and that wave function describes the locations of the electrons. It tells you the probability of finding an electrons at a certain location. And this is what ultimately tells you what the electronic configuration is. Now, electronic configuration, I'm talking about like the orbital structure, the s orbitals, the p orbitals, and so on. That's the electronic configuration. It's telling you where the electrons are in the material. One example of the solution to the Schrödinger equation is a one-dimensional potential well. So the first thing I want to note is that there are multiple solutions, and each of these solutions has a corresponding quantum number. When we solve, let's think back to your differential equations class. You can connect some of these concepts. Remember, in differential equations, depending on what order your function is, it may have more than one possible solution. Does anyone remember what they were called when you have multiple solutions to the equation? You have different functions that can be solutions to the equation. You may or may not remember this. This is one of the details. They're called eigenfunctions. Has anyone heard that term before? Eigennumbers and eigenfunctions? All right. Exactly. So if we're going to connect some of the concepts here, this is a partial differential equation. It has multiple solutions. Those solutions are called eigenfunctions. Mathematically, mathematicians refer to them as eigenfunctions, and each eigenfunction has a corresponding eigennumber. Now, in terms of what the quantum mechanics folks will say is that each solution has, instead of saying an eigennumber, they'll say each solution has a corresponding quantum number. Now, let's think about what physically multiple solutions means. So this is a one-dimensional example. Okay, One-dimensional example meaning instead of an electrostatic, a function of x, y, z is just a function of x. So this example here is showing a potential well. This is where there's a very high potential at x equals 0, a very high potential at x equals L, and then zero potential in the middle. Okay, so imagine that wherever there's potential, there's a lot of imagine a lot of positive charges at that point. That's one way to create high potential, a lot of positive charges. So the electron will actually end up getting stuck in this potential well. It'll stay in the middle here. We'll talk more about that later. But this is what the boundary condition looks like. The Schrödinger equation, you plug these boundary conditions into the Schrödinger equation. Again, you don't need to know how the solution was obtained. And then you end up with a wave function on the right side here. This wave function has multiple solutions. You can see this thing, it says psi is equal to 2 divided by L. L, of course, is a constant. N, a sine of n pi divided by L times x. X is the spatial coordinate. N are the eigennumbers. N equals 1, 2, 3, 4, and so on. So you have a series of sine functions which represent the solutions to the Schrödinger equation. All right, so if you see psi 1 looks like a sine wave. It's like half of a sine wave. Psi 2 looks like a sine wave with the same amplitude, but a higher frequency, smaller wavelength. And psi 3 looks again like it looks like another sine wave with the same amplitude, but in an even higher frequency. All right, this is all coming from the fact that this n can be 1, 2, 3, 4, 5, 6, and so on. So the higher n numbers, the higher eigennumbers, higher quantum numbers represent higher order solutions, higher frequency sinusoidal functions. So that's what it looks like mathematically. Now, what does the solution physically mean? Each solution corresponds to an energy state which can be occupied by an electron. Higher frequency solutions correspond to higher energy states. Let's connect this as well. We were talking about the Bohr model of the atom, right? Where the Bohr model of the atom says there's, electrons are orbiting the nucleus at different energy levels. Higher, you have n equals 1, n equals 2, and so on. Higher values of n correspond to higher energy levels, larger orbits around the nucleus, right? The Bohr model is nice because it's easy to understand. It's like a planetary model. It's something that's very intuitive. The quantum, it can actually help us understand the quantum mechanical model. The fact is still the same, that there are different energy states. They're not like circles. They're not circles like the Bohr model, but they do correspond to different energies. There's n equals 1, n equals 2, or different quantum numbers, and the higher the quantum number, the higher the amount of energy that it has. So multiple solutions means that there's multiple energy states, and electrons can occupy different energy states. Multiple solutions means there's multiple ways that the electrons can orbit the nucleus. The Bohr model says that all the electrons were orbiting in planetary orbits, like circular orbits. The quantum mechanical model will tell you that the shapes of these orbits are actually quite different. They form complex shapes like, if we just jump up here, they form like complex orbitals that looks like this. Some of them might be spherical, where the electrons are orbiting the nucleus in a sort of a spherical shape. And other ones might look something like this. They might be dumbbell shaped. Right? So these shapes are where the electrons are most likely to be. They're solutions to the Schrödinger equation, and they are telling you that the electron is most likely to occur within this dumbbell shaped region, for example. An electron at the second energy level, at the p orbital, will be likely to be in one of these dumbbell shaped regions. An electron at energy level 1 will be most likely to be somewhere inside this orange sphere. These shapes get more and more complicated as you go to higher energy states. This is a three-dimensional example of what we saw earlier. You notice that here, the higher energy functions were higher frequency sinusoids in a one-dimensional example. What we're going to see in the three-dimensional example is that the higher frequency solutions have more lobes. They're more complex functions. They have more complicated shapes. So the locations where the electrons are going to be, the definition is still the same. The electron is most likely to be within this region, let's say. Just the shape of the region looks a little bit more complicated. Let's back up for just a second here. Let's finish off this slide. So each one of these solutions corresponds to an orbital. That's the way that you can think about it. So going back to this one-dimensional example, the orbital is a region where the electron is most likely to be found. If we take this example here, if we choose an energy state n equals 2, so this is psi 2. This is the function shown in blue here. Okay, if we do that, then we can plot the probability density function psi squared. Okay, this is psi. Psi 2 looks like a sinusoid, as you can see here. If we plot psi squared, what happens if you take the absolute value squared of a sinusoid? Yeah, it just becomes above the axis. So that's what you're seeing here. All right, this blue line here is psi 2 squared. Like a sinusoid that's been flipped above the axis. This is a probability density function. So this means that the electron is most likely to be near L equals L divided by 4 or 3L divided by 4. If it's in the second energy state. Where is it likely to be if for the psi 1 function? Suppose it's an energy level, the electron is in energy level 1. Where is it most likely to be located? L over 2, right? You take this function psi 1, right? If you imagine taking the absolute value and squaring it, it's going to look very similar to psi, what it looks like right now. And the maximum value of that function occurs at L over 2. So the electron is most likely to be near L over 2. That's for the first energy state. But for the second energy state, it can be near either L over 4 or 3L over 4. So the shape of the orbitals will be different depending on what energy state it's located in. Okay, we just did this example. So in the example below, how many energy states can an electron occupy? How many different wave functions are there? There's 3. So there's 3 different energy states. And we did this example. We just looked at orbital psi 2. Let's look at psi 1. Where are we most likely to find an electron if it's in the n equals 1 energy state? It's going to be at L over 2. So the solution of the Schrödinger equation for a single atom, we need to find a potential field. Let's get into this. Let's get into this after we take the break. Let's take a short break, 3 minutes, just a stretch break. We'll do the 2 presentations, and then we will we'll continue and finish up this module. So we had these examples of the Schrödinger equation for a single dimension. So what does the Schrödinger equation, the solutions to the Schrödinger equation look like for a single atom? Let's go back here. So here's what we're doing. This particular example is looking at a single atom. So a single atom has a nucleus. And that nucleus may be positively charged. And so what does the electrostatic potential function look like in this case? We have a single charge.
0.
Where's the electrostatic potential the highest? we actually define electrostatic potential as, we define it in terms of the more, well, let me jump back here, so just to make sure we're not confused. In this particular example, we were showing the electron moving from a place where there's a bunch of negative charges to a place where there's a bunch of positive charges, right? The way that we define electrostatic potential energy is actually in terms of positive charge. So instead of looking at the movement of an electron, we had to look at the movement of a proton with the positive charge. The proton moving from positive to negative charge. It really is the same thing. It's just the signs are reversed. Okay. I was giving you this example of electrons because electricity is caused by the movement of electrons. So in this example, this part has a maximum electrical potential energy, but the sign of it is negative. Normally we define electrostatic potential energy as, if we would put a positive charge here, where would that positive charge go? It would move away. Just like the car rolling down the hill, that positive charge would get accelerated away from there, right? So we define electrostatic potential energy as, the way to think about it, if you were to put a positive charge at that point, would it have potential energy? And that answer in this case is yes. So the closer you are to this, there will be a large electrostatic potential here, a small electrostatic potential out here. The farther you go away, your electrostatic potential changes. So this function is V of r. It's a function of the radius from the center point. This is for a single atom, right? So the question that we're asking right here, conceptually, we're saying, okay, we have a single atom, a single nucleus. Where's the electron? What are the possible states that the electron can exist in? I'll write that down. This is where is the electron? What are its energy states? So we figured out this portion of it. We figured out the electrostatic potential boundary condition. So that's this V of r here that you see on the left. Okay, the mathematical function for it is that the electrostatic potential is a function of r. You can see that the r appears in the denominator here. Right, so r appears in the denominator. So at large r, the electrostatic potential quickly drops to 0. Now, if this boundary condition is plugged into the Schrödinger equation, then the answer that you get is what we see on the next slide. We'll show you that in a second. Remember that there's multiple solutions. Each one of the solutions tells you where the electron is most likely to be at that particular energy state. And the solutions look like, let me talk about this first. The solution is a set of three-dimensional wave functions describing the location of the electron. As before, there are multiple solutions, each corresponding to an energy state that an electron can occupy. And the orbital configurations that we saw earlier, we'll get back to that in a second. There's something called the Pauli exclusion principle that says each electron can occupy only a single energy state. It sort of makes sense, right? An electron can't occupy more than one energy state at a given time. The electrons always fill up the lowest energy states first. Things like to be at the lowest energy state. This is a general rule of nature. So if there are available energy states, the electron will tend to occupy the lowest energy state. The energy state is defined by 4 quantum numbers, n, l, m, and s. N is denoting the energy level, L and m are denoting the orbitals, and s is denoting the electron spin, which can either be spin up or spin down. So it's denoted by s equals plus or minus 1/2. The energy levels, going back up to the top, n can be 1, 2, 3, and so on. L and m represent the orbitals. So L can go from 0, 1, 2, all the way to n minus 1. So for example, if you are at energy level 3, then the possible values for L is 0, 1, and 2. So you can imagine that as you go to higher and higher energy levels, there are going to be more possible values for L. The quantum number m goes from negative L to positive L in increments of 1. So again, you can imagine at higher energy levels, there's going to be more available values of L. There are going to be more available values of m. And so you will have more orbitals at higher energy states. So these are what the energy states look like. The shapes of each one of the orbitals is actually determined by the Schrödinger equation. The Schrödinger function, that psi function, that will have the maximum large values in these regions that are shown here. So if an electron is at energy level 1, n equals 1, and it's at this first orbital where L is equal to 0, so this is called the 1s orbital. Okay. There's two different notations for orbitals, so just so you're not confused, I'm mentioning this NLMS notation here, but for the purposes of this class, we are going to use the 1s, 2s, 2p, those types of notations. We'll get into that in just a second. But I want you to see what the orbitals look like. In the first energy level, n equals 1, there's one possible orbital. Each orbital can hold 2 electrons of opposite spin up and spin down. And every orbital is assigned a unique number in terms of n, L, and m. But as I mentioned before, we are going to talk about these orbitals in terms of the other quantum numbers, s, p, d, f, and g. These are called the orbital configuration. It's a notation for that. So at energy level 1, there's only one orbital, and that orbital looks like a sphere. In the second energy level, n equals 2, there's an orbital that looks like a sphere. That's called the 2s orbital. And then at a slightly higher energy, you have the 3 different 2p orbitals. Notice that there's 3 p orbitals. Okay, one is in the x direction, one is in the y direction, and one is in the z direction. If I were to draw this out here, if this was, let's say this is the nucleus of the atom. An electron that's in the first possible energy state will be most likely to be in this region surrounding the nucleus, a spherical region. Okay. Suppose that energy state is filled. That orbital can hold a maximum of 2 electrons. The next possible energy state is, so that was the 1s that I just drew. The 2s also looks spherical like this. So this is the 2s orbital that I drew, slightly larger radius. Suppose that orbital is filled. Then the electrons start filling the 2p orbitals. There's 3 2p orbitals. There's one called 2px, and the 2px orbital might look something like this. The 2py orbital might look something like this. And the 2pz orbital looks something like this. Okay. So if we just look at one of them, let me redraw this. This is the nucleus. So the electron is highly likely to be in one of these regions if it exists in the 2px orbital. Okay, so there's 3 mutually perpendicular dumbbell-shaped orbitals. Those are the p orbitals. And then as we go to energy level 3, you can see that these shapes become more and more complicated. We won't spend too much time talking about all the different types of orbitals, but this gives you a general idea. Notation of energy states. So as I mentioned, there's 2 different languages for describing these energy states. The quantum mechanics folks use this NLMS notation, and the chemists sometimes use this SPDF notation. So I've included both here, so you have sort of a translation table here. The 1s orbital, the one that we saw on the first slide that looks sort of like a sphere, that has an n equals 1, L equals 1, m equals 0, and then s equals plus or minus 1/2. So that orbital can hold 2 electrons in that subshell. The 2s orbital down here has a quantum number n equals 2, L equals 0, M equals 0. So again, they can hold 2 electrons in a subshell. The 2p orbital has n equals 2, but then it has L equals 1. With L equals 1, the possible values for M are -1, 0, and 1. So the 2p orbital consists of actually 3 different orbitals. Each of those orbitals can contain 2 electrons of opposite spin, coming to a total of 6 electrons held in the 2p orbitals. All in all, the second energy level can hold 8 electrons. The first energy level can hold 2. If we go to the third energy level, it can hold 18. So the numbers increase as we go to higher and higher energy states. So this brings us to the electronic configuration for atoms. And this is the part that I think is relatively straightforward. To find an electronic configuration, first find the number of electrons using the periodic table. Fill the lowest energy states first, and fill a row with 1 spin before adding electrons of the opposite spin. This is the first energy band diagram that I'm going to show you. What is an energy band diagram? It shows where the possible energy states are. Okay, this one is just as simple as just a bunch of blank spaces. As you go upwards, those are energy states of increasing energy. Electrons prefer to occupy the lowest energy states first. So obviously the electrons will fill up these low energy orbitals before going to the higher ones. Yes?
But doesn't 4s fill up before 3D?
4s, that's a good question. I believe, let's look at this one.
There's certain molecules it does, but that has something to do with...
4s, yes, for potassium and calcium, you can see down here, the 4s orbitals, there's 2 4s orbitals that fill up before the 3ds. That's correct. So thank you for pointing out that mistake here. So just to correct this, so the 4s orbital should be somewhere in here. Okay? Now, when we fill up this electronic configuration, we fill electrons of opposite spin. So let me just do one example here. Actually, I believe this example is in the notes first. This is the electronic configuration of silicon. So silicon has 10 core electrons and 4 valence electrons for a total of 14 electrons. Okay, so all we're going to do here is do the electronic configuration for silicon. So let's do that real quick. All right, so we have the 1s. And then, so the first 2 electrons fill up the 1s. Now when we do this, we draw an arrow like this, and we draw an arrow like this. That represents 2 electrons of opposite spin. Spin up and spin down. Now, again, we're not describing the specifics of what spin up and spin down means. Each one of these electrons has a different magnetic moment. If you want to know the details of that, you can read more about it online, or you can take a course in the quantum mechanics. At a slightly higher energy, we have the 2s energy states. So then we fill up 2 more. Now silicon has an atomic number of 14, so it has 14 protons, 14 electrons. So we have 14 electrons that we need to take care of. So we have 1s, there's 2 electrons that go in there, 2s electrons that go in there. Then we have 3 2p orbitals. 2px, 2py, and then 2pz. Okay, so the electrons, the order of the electrons here, you first fill the orbital's spin up. So we'll fill in 3 electrons like this, 3 electrons like that, and then we go and we fill in the additional ones of opposite spin. Now, electrons, if an electron is occupied by, if an orbital is occupied by 1 electron, if the electron has the option of going into another orbital of equal energy and it's empty, it'll prefer to do that. That's why the electrons first go 1 in each orbital first, and then they fill up, then they go 2 per orbital. So now we've accounted for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Okay, so then we have the 3s there, and then the 3p. Okay, and we just fill in 2 electrons here. So this is the electronic configuration for silicon. The shorthand for this, let's say 1s2, 2s2, 2p6, 3s2, 3p2. This is just a shorthand rather than drawing the diagram. Okay, so the electrons fill up the lowest energy states first. 2 electrons per orbital. They fill in the same spin first if you're at the p orbitals and they're all at equal energy states. So pretty straightforward. Let's see here. So the actual, if we look at a diagram for the electronic configuration that you see here on the right, you'll see that we have the 1s state over here. Oops, oh, that's pen. Oh. We have the 1s state over here, and then we have the 2s state. Notice that there's a large amount of energy difference here. The difference in energy between 2s and 2p is relatively small. And then there's a big jump to the 3s and another big jump to the 3p. Okay, so even though in the example that we did, the spacing between the energy states were equal, in reality that's not the case. There's actually unequal spacing between the different energy states, just so you know that. Okay. Now, you can see here on the left, this is the Bohr model. Okay, the Bohr model was basically saying that you have electrons that orbit the nucleus at different energy levels. Okay, that's a nice way to visualize, but that's not actually the shapes or the regions that the electrons actually lie. Nonetheless, we can think of, we can again refer to the Bohr model and think of the fact that we have a lot of these electrons are at pretty low energy states, and a lot of the electrons here were at higher energy states. For silicon, for example, we had these electrons that were at the 1s and 2s energy levels, and then we had some electrons that are at the 3s and 3p orbitals. Now, the electrons here are said to be in the outer states, the valence electrons. Okay, these electrons are more active. The electrons that are at the lowest energy states, at the 1s and 2s energy states, those electrons are generally, they're happy. They're at a lower energy state. They don't tend to involve themselves in chemical reactions. You may remember these concepts from chemistry. The electrons in the higher states, those are the guys that tend to, they bond with other electrons, or they bond with other, those electrons are responsible for bonding between different atoms, as is the case with silicon. We'll talk about that in the next module. And that's a main concept that I want to cover there. You have the inner shell, the core or inner shell electrons here, and then you have the electrons that are occupying the higher energy states. Those are the valence electrons. Those are the more active ones. This shows the electronic configuration of other atoms. These are all the shorthand notations for them. The one that we did was silicon, so that includes the electronic configuration of all these smaller atoms, so 1s2, 2s2, 2p6. In addition to that, we add the 3s2, 3p2 in there. And this table sort of shows all of the electronic configurations for atoms from 0 through 24 in the periodic table. So for any given atom, you should know its electronic configuration in the SPDF notation. You don't need to know the NLMS notation. And I wouldn't expect you to memorize it. You know, if you know what the atomic number is, you should be able to write down the electronic configuration. So keep in mind that subtle point is that the 4s energy level is actually comes before the 3D energy states. Okay. Any questions? All right. So that is the end of Module 2. I'm glad we finished that up today. Keep on working on the homeworks for this module. We won't have a quiz on Thursday, but we will have a quiz the following Tuesday.
Those energy levels, that 4s filling up first, is only for certain molecules, right?
It's
I
for
thought there was-
potassium and calcium.
Okay, and those are the only ones that it fills up first. 3D normally comes first.
The 4s comes first in this case.
Okay, I remember from chemistry
Just a
that
second. Let me.
for I think 4 molecules or 6 molecules there was